Hi, I'm Paul, a field engineer. Nothing to do with fields, not a lot to do with engineering. I'd like to briefly take you through the journey from idea to startup, which is what Expo is, to show how AI can be harnessed effectively for penetration testing. We got where we are today in Expo from the culmination of our own development, but also the acceleration of AI capabilities in the frontier models, which you see so much about in the press. At Expo, we were excellently placed to observe and quantify this using techniques that go all the way back to the GitHub Copilot era, which feels like a long time ago. It wasn't that long ago. I joined GitHub just after Copilot really became a thing. The oldest part of the Copilot codebase was a collection of little coding exercises. That's how they made progress. At Expo, we used that same pattern. We started with benchmarks. As people have talked about, high school CTFs at first. As they've pointed out, those quite quickly maxed out. We ramped up to more realistic pen test scenarios. Now we're running on real customers. The pattern we see is that improvements come from structured challenges and evaluation, not just bigger models. This does lead us, though, to the evolution of the models over time. We can see that as the models improve, the output improves. We get faster and better as a consequence of model improvements. We have a chart here both of the solver success rate, which steadily increases over time, and a less steady improvement in speed over time. The rough evolution is from the days of GPT-3 and Codex, which could write code snippets that were barely usable. I remember having to really coax things and use a lot of prompting to get exactly what you wanted. GPT-4, which could solve harder problems end to end, and then we go through the familiar story of everybody who's used AI, particularly for coding. Sonnet 3.5 could start to plan. Then in 2025, we got something of an inflection point. We started to get agentic coding tools, which were producing a lot of unsafe code, but very quickly. That really created a sense of urgency around thinking about doing something about code security. We now have thinking models which now try to get information and plan sequences, not just answers. 2026 promises to be a similar acceleration in capability. We have this familiar cost and quality and speed triangle. And nothing is different with AI. Today you've got Anthropic, OpenAI, and Google models all jockeying for leadership, and I can't put any one of those at one of these corners and call it a day. Opus and GPT generally offer the best quality. Opus and Gemini give the best speed, and Gemini and GPT provide the best price. So it's one of those, like, who's winning? It depends on what you're doing. There is an underlying momentum behind all of them. Despite these differences, every kind of frontier model is improving over time. The message is that defenders must design systems, not bet everything on a single model or harness. And despite those differences, the models are all broadly good at similar tasks and also break in similar ways, which we'll look at now. We can divide the AI attack process into some phases, which are really familiar to anyone who's done human-driven pen testing. It's not a lot different. We need to understand the strategy and the customer requirements, plan the test, map out the target with some reconnaissance. Then we execute the test. We'll discover vulnerabilities and craft exploits for them, validate that they're real, and write up the findings in the all-important PDF of Doom, or maybe a bit more accessibly with an API. I'm sure if you've been a developer and you've got a pen test report inside, we're trying to make it less painful. There are naturally some cycles in this process. It's not just a waterfall, but schematically, that's what you're doing. We can restructure our table to highlight which phases are best for the AI, where the models do well, and where they tend to fall down. Where models shine on their own is this top set. We've got phases with a predictable nature. Payload shaping, exploring variants, spotting inconsistencies at scale, and generating reports. Where they break is in strategy, requirements, what is it supposed to be doing, planning over time, and also claiming success when they haven't even touched the system. They just hallucinate success. So it takes more than a model to make AI pen testing truly enterprise ready, really business ready, any organization ready. Let's have a look at the strengths in the attack chain. Where are LLMs strongest and why? We've got payload shaping and iteration after failure. It's a part where AI really shines. It excels at making exploits, bypassing filters, fine-tuning a payload to reach a goal. Failures give feedback, and that steers the model to success. That's clear not just in Expo, but in public examples that have been published with AI-driven attacks like the GTG 1002 attack. That was a mouthful. They really need nicer names for these things. Just like CVEs, you can't remember CVE 2026, whatever. Give it a nice name. I know people hate them. But, detecting patterned inconsistencies across a lot of data is another AI skill. Something that stands out as different in one place can be attached to and used as a clue to a vulnerability, such as a missing check somewhere. And generating clear output is also a strength. Summarizing and explaining are some of the things that large language models are built for. They're the major tasks that they are trained on using reinforcement learning. AI can do most, if not all, of the work here, and I think that's been recognized quite widely. These are places where there's strong intrinsic feedback in the work and recognizable structure with sufficient training data in the models. Where LLMs are weak is where you've got a lack of good feedback and just the way that LLMs work. State tracking, long chains of reasoning, the models can get confused and a bit hopeless. Helpless, both. Misinterpretations, in particular, can cascade through a chain of thought and lead to dead ends. Non-determinism is famously a part of LLMs. Even when the temperature is set to 0, because of the way that the models work, you can see inconsistencies. Planning drift happens when the model happily drifts off task, picks up a new task halfway through, and doesn't do what you set it to do. We have got models lacking governance and guidance. They'll forget or disregard constraints that they are given. Do not ever do this. And then, as we've seen with prompt injection, bypassing safety, even not under adversarial conditions, LLMs don't stick to the task. They forget the guidance. And perhaps worst of all, as I mentioned, models can make completely unfounded "I did it, I solved the problem" claims without even touching a system. These are some of the reasons why raw agents are dangerous in production pen tests. If you're as old as I am, you might remember Magic 8 Balls. It is certain. Yeah, LLMs aren't quite as unreliable as a Magic 8 Ball, but they can very confidently state certainty when there is no such certainty. So you have to have some way of checking their work. Credit for the photo goes to Xanology, taken via Wikimedia. Resolving this unreliability takes work. We've got what we're calling here version 0, a moonshot. I don't think actual moonshots are in one step. There's quite a lot of work in NASA actually getting somebody to the moon. But we're calling it a moonshot anyway, you know what it means. And This is the idea that you can just prompt the LLM with a goal. Say, go find everywhere that one user can access data that another user can. It guarantees loads of noise and untrustworthy claims. Version 1 adds an after-the-fact validator, an adversarial LLM, to double-check these claims and see if they're true. But it reduces false positives. The task is still a long shot, so there's a question of can you reach it? And if the validator is an LLM, it can be deceived or it can get things wrong. Version 2 is around where Expo is now. It means that we break tasks into small, structured, verifiable hops, generate leads looking for suspicious behaviors, response differences, and then run targeted attacks on those leads. Really importantly, we use validators that are certain. If I've definitely accessed something, I have definitely accessed something that I couldn't before. Each hop in the work is groundable and testable. You can reason about quality because it's a small amount of work being done at each stage. This is where AI meets real security engineering, and it's the backbone of how Expo works. We can give an example of how Expo can go wrong. We've got an objective to get a file read vulnerability. I'm not expecting you to read through the whole thing. Looking for problems in Akamai Cloud Test, and we've got a few examples of how to do a file read vulnerability. It's looking quite promising so far. We get unstuck quite quickly. It's immediately talking about a known XXE vulnerability in Cloud Test and giving a number, and then talking about how it's going to exploit it. If we have a look at the actual CVE, it's not in that software at all. It's completely hallucinated it, and we are going off on a dead end completely immediately. It claims to have done a quick search. Did it do a quick search? No, it did not. That's an example of just how if we took this at face value without any validation, then it leads us seriously astray. A lot of people are pitching AI agents as pen tests. And we've seen one reason why that's dangerous. We can run through some more. Safety. You can't have an agent free firing at production or even staging without some guardrails. Determinism and reproducibility. You've got to be able to replay findings and understand what the agent was doing. And enterprise trust. You need evidence, not vibes, to convince engineers to take work to fix things. Our approach is to take the creativity, the power of models, amplify it, and then bind it tightly to reality with validators and orchestration. AI pen testing without coordination is chaos. Let's look at the details of how Expo goes about replicating what pen testers do. So in our pre-flight, we map out the application's terrain. We are checking that we can authenticate cleanly if we've got credentials, and gently mapping out how the application works before we do any attacks. Once we get going, the coordinator manages and delegates tasks. It's a conductor to get a harmonious outcome. It maintains a global view, identifies the attack surface, and directs testing, debriefing agents, refining findings, and prioritizing what comes next. The individual solver agents, these are the things that actually do the focused, short-lived work. That's more mapping or specific attacks. And then validators are used to verify that the findings of the solver agent are actually real, as deterministically, another tricky thing to say, as possible. For example, for an authorization bypass like an IDOR, then we want to validate that we really can see something that we shouldn't be able to. If we have a look at that pre-flight in more depth, the user can define target endpoints, give authentication context, talk about which assets are in scope versus not. It's all under the control of the user, and other test parameters that help keep things on track. It creates rails. The solvers can be created within these bounds, and validators know exactly what proof means. This is where compliance requirements can be respected as well. The safety posture is set before we let the solvers and the agents loose on the environment. Talking about the solvers in a bit more detail, these are like a specialized pen tester. They're told to go looking for just one thing. That's all they care about in life. They're a pen tester who only cares about finding SQL injections. That would be a bit of a strange person, but in this case, it's a completely valid approach for the agent. Recon is used to enumerate endpoints, and they're given prizes if they succeed, and there's all sorts of different ways to orchestrate agents to explore wide or deep to make sure that we cover the full attack surface. We've got probing to look for threat surface and form a bit of a threat model of what can I see from different accounts under normal use before I try attacks. And then there's vulnerability and exploit solvers that are there to take all of that context from the recon and understanding the threat surface to find those vulnerabilities and provably exploit them. They're run concurrently, they pivot on feedback, and they escalate information up to the coordinator only when validators confirm that findings are real. What does it take to build a great solver? You need data, evaluation harnesses with continually improving benchmarks, and tight integration with validators. This is why you can't just use an AI to do pen testing. Validators are what keep Expo truthful and honest. They take these agent outputs, check them for evidence of real exploit, show an impact, and produce ground truth that a real vulnerability exists and a way to reproduce it. That's what makes what we've built reliable. We can take a look. Just checking time. I'm fine. It's a busy slide. We can take a look at our IDOR detections and validations, just as an example of how we do this process to finish off with. Our solvers iterate through different variations, exploring what should and shouldn't be accessible, and set about trying those permutations in attacks. Once a problem is detected, the validator steps in. At the top, you can see a canonical IDOR pattern. You've got two successful requests to a unique resource, but they're from two different identities. We expect to be denied for the unauthorized identity, but we observe user A's data even when we're operating as user B. And we've done enough of a threat model to understand that that's not normal. Clearly, if you do this on social media and start saying, I've got an IDOR because I can see your posts, that's the whole point of social media. So the threat model is important. Our reports embed the full thinking and result traces plus code to reproduce, like I talked about, so that you can follow along how it was discovered, what different things were done along the way, and how that final solution was created, which can be really useful for getting your head around, is this real, even when you see the script and you see the output. This demonstrates how the AI creativity plus the human design validation combine. And this isn't theory. We've done this on real customers. On our blog, you can read about how we found an idle vulnerability in Spree during a customer assessment, and then we responsibly disclosed it because it's an open source project. A lot of the time, the vulnerabilities, the 0 days that we find, are just reported straight to the customer. It's their own proprietary website, and they fix it. We've also got examples of remote code execution in Bing that Microsoft fixed. there's more examples on our blog if you're curious, including snippets of traces, so you can see the kind of thinking in inverted commas, that the AI did while it was operating. Thank you so much for listening.